let's talk about a fundamental rule of engineering. It's a principle written in steel, something that governs some of the largest structures you'll ever see, and it explains a critical design feature that, honestly, you've probably never even noticed. So let's get right into it. You've definitely seen these things, right? Driving down the highway, you pass these massive industrial storage tanks. They hold thousands, sometimes millions of gallons of fluid. But here's the thing, they aren't just giant cans. No, these are precision-engineered vessels designed to contain absolutely immense forces with total reliability. And that precision brings us to a really critical question. If you could get up close, you'd notice something strange. The steel plates making up the tank's wall, they're a lot thicker at the bottom than they are at the top. Now that's not a mistake, and it's not a cost-saving measure. It's a vital design feature. The real question is, why? To figure that out, we have to start with the single most important variable in this whole puzzle: pressure. You know, in engineering, we think of pressure as the amount of force being pushed against a specific area. It's kind of like the invisible enemy that every single structural engineer is constantly fighting. And this little equation right here, this is the fundamental tool we use to pin it down. Pressure equals force divided by area. This simple ratio, it's the absolute bedrock of structural design. If you want to build something that won't break, you have to understand the pressure it's going to be under, period. Okay, now for a fluid that's just sitting still in a tank, what we engineers call fluid statics, a more specific equation enters the picture. This is the law of hydrostatic pressure. Now, I know, it might look a little complicated, but trust me, this is the key to everything. For what we care about, the forces pushing on the tank's walls, we can actually simplify it down to its most critical parts. So let's break this down. P is the pressure we're trying to figure out. That squiggly rho, that's the fluid's density, basically how heavy it is. G is just the constant pull of gravity. And H is the height, or really the depth of the fluid. Now think about it. For any liquid in a tank, its density and the pull of gravity are constants. They don't change. That leaves only one variable that truly matters here, and that's H, the depth. And this right here is the aha moment. Our equation tells us that as H gets bigger, P gets bigger in direct proportion. It's a one-to-one relationship. For every single foot you go down into that fluid, the pressure pushing outwards on those tank walls increases by a set, predictable amount. It's just a relentless, linear climb. And this chart just spells it out perfectly. At the very top of the tank, where the fluid depth is almost nothing, the pressure is super low. In the middle, it's higher. And way down at the bottom, where you have the entire column of fluid pressing down and out, well, that's where the hydrostatic pressure is at its absolute maximum. So the tank wall has to be thickest there to contain that force. It's not a choice, it's a physical necessity. Okay, so we've cracked the why, but this principle, it's not just about building a tank efficiently. It's about something way, way more critical: safety. Because in the real world of engineering, you have to remember, not all fluids are created equal. Let's just circle back to our equation for a second and look at rho, that fluid density variable. Water, as you can see, has a density of about 1,000 kilograms per cubic meter. But now look at sulfuric acid. It's almost twice as dense. That means for the same amount of space it takes up, it's nearly twice as heavy. And here's why that is so incredibly important. Let's say you have a tank that was perfectly and safely engineered to hold water. If you turn around and decide to fill that same tank with sulfuric acid, you have just almost doubled the force that's pushing on the walls at every single level. The entire structure would be critically overstressed, and you'd be risking a catastrophic failure. Engineering is and always will be a science of specifics. Look, this isn't just some abstract theory from a textbook. It's a core rule of professional practice. As this quote says, knowing the exact properties, the specific gravity, the density of the fluid you're trying to contain is completely non-negotiable. It is the absolute first step in making sure a structure is safe and fit for its purpose. So the next time you see a massive dam holding back an entire lake, or you think about the incredible forces trying to crush a deep-sea submarine, you'll know the fundamental law that's at work. It's a simple, powerful truth: depth dictates design. Now that you see it here, where else in the world are you going to spot this principle in action?